Okay, so this is the final section before we take our first quiz on this chapter. So these first three sections on tangent properties, chord properties, and now we've got a section on arcs and angles. So this will go into our circle properties standard on the first quiz, which we'll be taking next week. So our goal today, discover relationships between an inscribed angle of a circle and its intersected arc. So in class today, we would have started off with this one. One of the big things that we've been talking about here in this class is anytime you have a radius of a circle, you've got congruent lines. And so this is an isosceles triangle. If we've got 51 here, we know we've got 51 here. And we can use our triangle sum conjecture to find this angle here. We just take 180 minus 51 minus 51, and we'll get 78. So that angle is 78. And then to find x, we just need to do 180 minus 78, and that's 102. Now, we'll look more at some things going on here in a little bit, but one thing I will have you know is to take a look at how 51 here and 102 relate to each other. What's the relationship between those two angles? That's what we'll be looking at. So before we get started, yesterday we talked about what an inscribed angle is. It's an angle with its vertex on the circle whose sides are chords, meaning that they go through the circle. Those sides could obviously extend outside the circle, that would be fine, but they have to go through the circle. You can't have an angle with just a vertex on the circle and then its side going off out of the circle like that. So we're first going to look at what the measure of an arc intercepted by an inscribed angle is going to be. We know that the arc and the central angle are the congruent. What about the arc compared to the inscribed angle? So I've got an exploration here to do. Hopefully you've seen kind of on this one here, this central angle is 102, which means this arc is 102, and that angle there is 51. It's exactly half of 102. Let's see if that always holds up. So here I've got a circle, I've got my inscribed angle, and I've got my central angle, which is the same measurement as my arc. You can see right now 108.1 and 54.1 within a rounding error, that's half. And as I move these around, you'll see, okay, 66 and 33, 175 and 92, that's half as well. 151 and 70, almost 76, that's half. You know, within rounding, they're obviously rounded, but it's always going to stay half. 104.5, 52.25, always half. And so our conjecture here for this one is going to be the measure of an angle inscribed in a circle is half the intercepted arc. And importantly, to go along with that, it's also the central angle that goes along with it. If you take those two same points here, C and R, and make a central angle out of it, that central angle is going to be twice that inscribed angle. So the conjecture in the book only mentions that it is half the intercepted arc, but because the arc and the central angle are the same, the inscribed angle is also half of the central angle that has the same, that intercepts the same arc, that has the same two endpoints on the circle. Now, these next two conjectures here, I'm going to say are optional as far as writing down. And that's because they're pretty direct, directly follow from this conjecture. If you know this conjecture well, there's no reason to write down these next two. And we're not even going to do an exploration on these. We're just going to take a look and kind of think deductively about this. So inscribed angles that intercept the same arc. So here I've got angle P and I've got angle Q. They both intercept this same arc, AB. It's a major arc in this case. And so since that arc is just one arc, obviously it's the same measure for both of those. And since P and Q, each of them are half the measure of this arc, whatever this arc is, P is half of it, and whatever that arc is, Q is half of it. Well, they're both half of the same thing, so they've got to be the same as each other. They are congruent. It would be the exact same thing for central angles, except you can't have multiple central angles that intercept the same arc. So because they intercept the same arc, they are congruent to each other. Another one that kind of relates to the same idea, if we inscribe an angle in a semicircle, so here we've got a semicircle with an inscribed angle in red, what do we think the measure of that angle is? Well, it intercepts a semicircle, and we know a semicircle is 180 degrees. And since our inscribed angle is half of that, it's going to be 90 degrees. Again, that's not something I think is super important to write down, because as long as you knew that first conjecture, that the arc is always twice the inscribed angle, or the inscribed angle is half of the arc, well, there's 180, half of that's 90. You don't really need this conjecture. Okay, there's two more. These ones are not optional. You need to write these ones down. Next up, we've got cyclic quadrilaterals. So before we get into that, a cyclic quadrilateral, this word you see here, just means a quadrilateral that can be inscribed in a circle. Not all quadrilaterals can. If you think about something like a general parallelogram, that's not going to be able to be inscribed in a circle. But in this case, we're going to be looking at what we know about the opposite angles. And first, we'll start off with an exploration here, and then we might talk about why that might be true deductively. That is the wrong one. Sorry about that. This one is the right one. So here I've got a quadrilateral inscribed in my circle, and you can see I've measured two of the opposite angles. One thing you'll notice here, unless I can move C wherever I want. It's B and D that actually make a difference in what angle C is, because no matter how I move C, it's still intercepting the same arc, so its measurement's still the same. So if I move these around a little bit to make numbers that are easier to figure out, try right about right there. That's close enough. We've got 99.9 and 80.1. If we add those up, you're going to see they add up to 180 degrees. It doesn't matter where I put these. The addition is going to get a little harder. 117 and 63 still adds up to 180. No matter what I do, those angles are always going to add up to 180 degrees. I'll make that one. There's one. There's 150 and 30, so they add up to 180 degrees. So in this case, in a cyclic quadrilateral, or any quadrilateral that can be inscribed in a circle, the opposite angles are supplementary, which again means that they add up to 180 degrees. You can put whatever one you want in there. Your definition, not mine. So go ahead and put that in. And then we've got our last one, and that is the parallel lines intercepted arcs conjecture. So this one is a pretty specific one. You've got a circle with two parallel lines that go through it. Lines that go through circles like this are called secants. Not a super important word that you know, but we've got two lines. They are parallel and they intercept the circle. And we're going to be looking specifically at these two arcs. When I highlight them, you might have a pretty good guess at what's true about them, but let's go ahead and take a look at what happens here. So here I've got a dynamic version of this that moves around. I can change the distance between them, all sorts of fun stuff here. And we'll just go ahead and show the arc measures. Remember, the arc measures are the same as the central angle, so I'm really measuring the central angle measures here. And you can see that they are equal to each other. It doesn't really matter what I do. They stay equal because the lines are parallel. Now, why this is true is a good one to kind of think about some of the stuff we've learned already. If I draw in this line here, those two angles there are equal because they are alternate interior angles. And if you look at it, if those equal angles intercept arcs, this equal angle here, which is an inscribed angle, intercepts arc EC. This angle here intercepts arc BD. And since those angles are equal, the arcs are going to have to be equal as well. So that's kind of where we're coming from with why that one has to be true. Now, something to be careful of there, just because the angles are equal, this is working because these lines are, in the same position. It wouldn't be true if it was just any equal angles throughout the arc, I don't think. So be careful a little bit with that. But that's why this one's going to be true. So parallel lines intercept congruent or equal arcs on a circle. And it's the ones that are between the two parallel lines. This one's not going to be a super important common one, but it will show up. Now, a couple of questions here, just to kind of make you think about some things. what kind of quadrilaterals can be inscribed in a circle, i.e. which ones are cyclic? So think about that. What kind of quadrilaterals can you put inside of a circle and actually have the four corners touch the circle? Okay, so a lot of you hopefully thought about squares. Absolutely, squares are going to work. Rectangles, all rectangles are going to work. Then we took a look at things like parallelograms and rhombuses. Now, parallelograms and rhombuses are going to work if they're rectangles, but otherwise they're not going to. Oops, that's not the right thing. So if I draw something like this, here's my circle, and I take a parallelogram and I try to inscribe it in this circle, what you're going to see is, I can get two corners to touch pretty easily, but then those third and fourth corners don't want to be so nice. So parallelograms are not going to work. Trapezoids, certain types of trapezoids will work. Certain types won't. In this case, I can make this work by stretching it out, basically treating the two parallel sides like chords, one closer to the center than the other. So some trapezoids can, again, some can't, not all of them will be able to. Other types of quadrilaterals that might be able to work, just kind of some general, like kites. Kites can pretty much all work. And other types of just irregular quadrilaterals are going to work too, as long as you can put the points on the corners. But for sure, all rectangles and all squares will work. Now, so examples that you're going to see are going to look a lot like this. This one's a pretty complicated one where they're asking you to find a lot of information, but each individual part isn't going to be so bad. One thing you're really going to want to do is, again, draw the picture and write in the things. So here it says that arc AB is 70, so I'll put that there. Arc CD is 15, so I'll put that there. Arc DE is 65, so I'll put that there. Measure of angle ABF, so A to B to F is 62, so I'll put that there. Then it's just a matter of kind of going through and starting to find the things that you can find using the different conjectures that we learned about. So one thing I'm seeing here is this angle 62 is an inscribed angle. So I can use that to find this arc. It's just twice that. So 62 times 2 is 124. So I know that arc is 124. Next thing I might know is, well, these lines are parallel. If this arc is 15, so is this arc. And now I've got all the pieces of the arc except for that part BC. So I know the total of that arc has to be 360 degrees. So I can just take 360 minus 70 minus 124 minus 15 minus 65 minus 15. And what's left over is 71 for that last arc. So BC has to be 71. EF, we found that, is 15. And then we've got to find BAC. Well, BAC, it's this angle. From B to A to C, that's this angle here, is just half of my intercepted arc. Well, I can just take 71 divided by 2, and I get 35.5 for that arc there. Final example here, we've got a circle, like so. And we only know one of these angles, but we know lots of other things about this picture. Biggest thing is the fact that these two are radii, which makes this little triangle here isosceles. So if one is 43, so is the other. Now I can use this triangle to help me find this central angle at O. I can just take 180 minus my 43 and my other 43 and get 94. Not 84, 94. And if the central angle is 94, the inscribed angle here has got to be half that. The arc matches the central angle. The inscribed angle is half of the arc. So if the arc is 94 degrees, central angle is half of that, and 94 divided by 2 is 47. So x has to be 47. So all the math you're doing, again, is going to be really straightforward. It's addition, subtraction, maybe some division. The challenge here is using those conjectures to figure out what you know, and focus on finding just anything that you know right away. You can always find something using one of those conjectures, one of the things you know, then use that new information to build on what you've got to find. So homework today here is page 468. You're going to do 1 through 6, 8, 10, and 15. 1 through 6 are definitely ones I think everybody should be able to do. They get a little bit harder here. 6 is a really good question. Think about what you would know here, like combining things together, right? Here you've got a cyclic quadrilateral. So what's that tell you about opposite angles? And then when you combine, like this angle here is this arc plus this arc together. Number 8 is a rectangle. So what you know about rectangles is the sides are parallel. So you can use that parallel lines conjecture. K actually goes back and even uses some things that you learned about last section. If these two chords are equal, what's that tell you about those two arcs? Can you find that one? And then 15 is definitely a little bit of a challenge here, but I want you to give that one a try. Biggest thing to know here is that these lines do not go through the center of the circle. So you're using these inscribed angles, these are not central angles. So give those a shot. The answers are in the notes down below, and you can check those after you've given everything a shot.